So let's talk about the magnetic field. We all know about magnets, and I'm sure you've all played with magnets at some point. So let's talk about a bar magnet that floats in water. So let's first draw the water. Here's some water. That's what it is. We can put like a little magnet maybe floating on a cork or something sitting in the water. And let's assume that the way that we're oriented, this over here, this is north, okay? This is south, this is east, this is west. What do you expect this bar magnet to do? Well, we expect it's going to rotate until it points towards north. And, you know, in common terms, we call this a compass. But there's some other characteristics of magnets that are interesting. So one of the things that is useful about magnets, we know that the like sides repel and the unlike sides attract. Okay. The other thing is if you cut a magnet in half, you don't get one magnet that's north and one magnet that's south. You end up with two just smaller north-south magnets. All right. So magnets have two poles, therefore they are a dipole, and you can't separate the two poles. You can't cut them. So this is a little bit different than charge, where your dipole can be broken into a positive and negative charge. What kind of things can magnets attract? Well, this, no. How about this? No. How about this? Yes. And it also turns out it doesn't matter which side of the magnet you put towards the paper clips, they're going to attract either way. So magnetism is a long-range force, meaning you don't have to actually be touching anything for it to work. So just to think back to a force that we already know that's long range, well, we've talked about gravity, but also the electric force and therefore the electric field. Because if we have an electric force, it comes from an electric field. You can assume if we have a magnetic force, it's going to come from a magnetic field. So reviewing what we know about the electric field is going to help us understand the magnetic field. So in the case of the electric field, we had this inverse square law for these 2 points, okay? The force between two charges, Q1 and Q2, separated by this distance, R. We could call this an electric field. This is the force. All we did was get rid of charge 2 to get the field. And we know there's a relationship between electric force and electric field. So remember the electroscope. The electroscope was this metal ball, okay? And it had these leaves hanging out. Ours looked a little bit different, but same basic idea. If you charge this, or if you polarize the charge from here to here, you end up with a repulsion. Now, if you put a magnet near this thing, turns out nothing happens. So I'm just telling you about this because this is how we know that magnetic fields and electric fields are different phenomena, okay? Remember, if we put a charge near this thing, you end up with these leaves in the bottom moving apart. They're going to repel, okay? This is not the case. You can touch a magnet to this all you want, and it's not going to change how these leaves behave. Now, probably if you put the magnet over here, you could attract one of the leaves, but it's still a different phenomenon. Putting the magnet up here does nothing to the leaves down here. So magnetism is different from electricity. Okay, so let's talk a little bit more formally about the magnetic field. So remember, still going back to the electric field, we know that all magnetic poles are dipoles. Now, that's not true of the electric field. We can have electric monopoles, meaning we can have a plus charge or a minus charge all alone. But for the magnetic field, a plus charge and a minus charge, meaning these can exist alone in an electric field, but north and south, these are always together. You cannot cut this and get a north and a south. So, thinking about what happens when we put a dipole in an electric field, if you put this dipole here, it's going to line up with the electric field. Well, if you put a magnet in the electric field, not a whole lot's going to happen. But remember, if you put a compass, which is a magnetic dipole, in a magnetic field, then you're going to get the same phenomenon. It's going to line up with the field. So remember, the direction of the magnetic field is the direction that the north needle points. And magnitude of magnetic field is proportional to the torque that the needle feels. So this tells us the direction. How fast it turns tells us the magnitude, because remember, these things are vectors, okay? So the magnetic force, which we would call FB, that is going to be a vector. All right, so the compass is a magnetic dipole that can tell us the direction of our field, and if we could measure how fast the compass needle is turning, and you'd probably have to also know its mass, that's going to tell us the magnitude of our magnetic field. So slow turn means not very strong field, fast turn means very strong field. Now, how did we discover the magnetic field? Well, the first references to magnetism came in about 100 BC, which is pretty old. And the first compasses were about 100 AD. Basically, people had these rocks that were mostly iron, and they would hold them when they were out at sea, and they would see if they'd turn. And they were basically doing exactly what we did in the first slide, floating a magnetic-y rock in the middle of a puddle and seeing which way it turned, and that would give you the direction that you needed to go. So this is a torque issue. Here's your pivot point. You have forces on either end of your dipole, and then this thing's going to turn to line up with the magnetic field. So magnetic dipoles align with the magnetic field, and we know the magnetic field points away from north, and the magnetic field points away from north magnetic poles and towards south magnetic poles. And we're going to deal with field lines again. Now remember, when we talked about field lines for the single pole, the monopoles of electric field lines always started at positive and ended at negative. But remember, we didn't have dipoles in that case all the time. So this is going to change things. On a separate side note, the magnets we use for compasses are a little bit confusing. So this is our geographic North Pole. Here's our geographic South Pole. But you'll notice that the pole here, where the magnet actually points, right? If you have a compass needle, it's going to point that way. That's going to point to magnetic south, because of course you know that the north pole of a compass needle is going to point to the south pole of a magnet. That means what we think of as geographic north is actually magnetic south. Well, this is the magnet. Okay, this is the north pole. This is the south pole. What do we call something with two poles? Dipole. A dipole. Okay. Can magnets come in monopoles? Not that we know of. Okay, and probably not at all. So, at least unless something like really funky is happening, like at a quantum level or something. I don't know. Anyway, if you put a magnet anywhere near this other magnet, if you put a compass anywhere near this magnet, it will move itself if it's allowed to move, so that the north pole of your compass needle points to the south pole of your magnet. Okay. You'll notice that these little compass needles always point along the magnetic field lines. Now, we've talked about electric fields, right? We're now going to talk about magnetic fields. They have a lot of similarities, okay, but they also have some differences. The main difference between a magnetic and an electric field is a magnetic field is always some sort of loop, okay? And we'll talk about what that means in a little bit. Whereas, remember, electric fields can start at some point and just go out, and they don't have to end anywhere, okay? They don't have to come back. So they diverge, right? They go out and they can be like spurs. They can go out into the world and just not come back. Magnetic fields are always big loops, so no matter how far they go out, they always come back, okay? So we're going to sort of sketch out what the magnetic fields lines look like using a compass. Now, when I say diverge, can you think of a math word that sounds like diverge? Maybe you heard it? Divergence, okay? So, if just as a preview for vector calculus, electric fields demonstrate divergence, okay? Which means if you create a surface, like a Gaussian surface, the flux can be non-zero.
meaning electric field lines can pierce it and not come back, okay? So they can go just one directionally. If you have loops and you create a closed surface, right, what is your divergence? 0, because everything that goes out has to come back in because circles, okay? So the magnetic fields have 0 divergence. Electric fields can have a finite divergence, okay? And that's the big mathematical difference from them from a vector calculus perspective. And this is why we use vector calculus to talk about electricity and magnetism, because of these really basic things. So the geometry of magnetic fields is really different than the electric field. And so we're going to be dealing with something that's called curl, okay? And when you think of curls, things are round and loopy, okay? So magnetic fields are round and loopy. They exhibit curl. Electric fields actually have divergence and curl, but we haven't really talked much about the curly types of electric fields, but we'll talk about them when we get to inductance, okay? Just as a question, what was the way we created electric fields? How do you get an electric field? Yeah, it's related to the electrostatic force. So if you have an electric field, what can you assume you have? Charges, right? So the main way we've talked about creating an electric field is some charge distribution. So you have some positive charges or negative charges, you have an electric field, okay? Magnetic fields, so far we've only talked about creating them with magnets, okay, which is a dipole. So charge can be plus or minus. Magnets are north-south, but they're always stuck together. Okay, so anyway, let's put some more compass needles around this thing and see what they do. So we're going to put a bunch of needles, and you'll see a pattern forms. Okay, and this looks something like this. And if you ever played with magnets and that like iron ore, like little, what are those, like little shavings, like iron shavings, you can see this pattern. It looks something like this. Okay, but if we go back, oh no. Should not have done that. All right, you go back, you see the magnetic field lines point from north to south. Now remember, I said these are loops. So what does that mean? What are we missing? Which way do the magnetic field lines point inside the magnet?
To the right, three.
Yeah, so basically this would be a loop that looks like this. Okay, so these loops, they come in and they actually go all the way through the magnet. Okay, so all of these magnetic field lines, if you drew them out as far as you could, right, even these, they're going to loop way out and come back and go through the magnet. Okay, so magnetic field lines are always closed loops. All right, whether or not you have the space or the need to complete the loops, that's different. But you have to think about these things in your head as connecting back up again. Okay. All right. So that's what that looks like. Here's a question. Yay, okay. Yes, it points up. Why?
Because north
It's
attracts
the north
south.
side of the needle, right? And it points towards the south end of the magnet. All right? Okay. So the discovery of the magnetic field, this guy, I mean, speaking of rich people who got to go to college, you get to wear medals and stuff. Hans Christian Ørsted, okay? This is one of the first machines that discovered magnetism. Basically, this is a compass, right? And here is a thing that he hooked up to, I guess, a battery. I don't even know if they had batteries then. But anyway, here, this is essentially what the experiment said. So, if you just put a wire, let's say, imagine this wire is actually connected to something, okay? And you just have a little plate where you set a bunch of compasses here. Which way do the compasses point?
Towards it.
Well, no, towards what?
Center of it.
Well, no, there's nothing going through this wire. It's just a piece of metal.
North.
It's just like if you put a compass down, where does it point?
North.
North. Okay? The compass should point to geographic north. It's the Earth's magnetic south pole, but it's geographic north. Okay? So all of these things point north with no current running through this thing. Now let's say we connect this up to a battery, maybe a resistor, run a current through it. What happens to the compass needles? Do they still point north? No. It turns out they actually point in a lovely circle around this wire. Okay? Now what do we know about which way the compass needle points? What does it align with? The magnetic field. Okay? Which means, before we turned on this wire, the dominant magnetic field was from Earth. Okay? After we put current through this wire, the dominant magnetic field is probably not from Earth. Where do you think it's coming from? The wire. Okay? So in both cases, there's charge in this, right? It's probably neutral, same number of positive and negative charges. But we also know that if we have an electroscope and we put charges on it, right, it doesn't behave the same with magnets. You can have like something that has an electrical charge and it's not attracted to the magnet, right? These are different things. So magnetic poles and electric poles, not the same, okay? But it turns out when we move the charges, then we get something interesting, okay? So magnetic field can be caused by permanent magnets, like we're used to, like refrigerator magnets, but it can also be caused by electric current, okay? So we've just spent a lot of time talking about how to generate electric currents and how they behave in circuits. Now we know they also generate magnetic fields, okay? Not super big magnetic fields, but compasses were the first use of the magnetic fields, but nobody really worried. At least we don't have any documentation of anybody like considering philosophically why compasses worked. Everybody was like, oh, these rocks point north. Yay, now we won't have to die at sea as much, okay? But in the 1800s, they discovered that you didn't just have to have the magnetic field from the Earth. There were other ways to create other magnetic fields, and it was mostly because we started dealing with electricity, okay? So currents, electricity doesn't show up till the 1800s, so we don't notice this phenomenon until the 1800s, all right? So currents also create, sorry, I had some note to talk about Lost, but I can't remember what that show was about anymore, so, I created these lectures when it didn't suck, and also before it ended. Oh, sorry, it's not later. Just spoiler alert, it's going to be terrible. Yes, so they couldn't really have discovered that currents created magnetic fields until there were currents that people saw, okay? So the magnetic field is represented by a B for magnetic field. Yes, it's very easy to remember. It's just like the electric field. It's created at all points in space. It surrounds moving charges or permanent magnets, okay? It's a vector. It exerts force on dipoles, so basically compass needles, all right? So everything's kind of a compass needle. And here's some standard magnetic field strengths. Now, the magnetic field strength is measured in units of what? There's a T. Guess what it stands for? Tesla. Yeah, that guy has hands and everything. So, here are some field strengths in units of Tesla. Sometimes we also use Gauss. Maybe you've heard of him. He had that law. But there's a conversion between Teslas and Gauss. So, field strength, 5 times 10 to the negative 5. So, the magnetic field strength on Earth is pretty small, okay? Which means that anytime you have something like a current-carrying wire, you can overpower the magnetic field strength of the Earth, okay? Even just a refrigerator magnet is 2 orders of magnitude bigger than the magnetic field of the Earth, all right? Laboratory magnet is about 1/10 of a Tesla to 1 Tesla. A superconducting magnet is about 10 Tesla, okay? And usually, and these are just all permanent magnets, okay? Well, although, fun fact, we're not 100% sure what causes the magnetic field of the Earth. I mean, there's a lot of like hand waving, like molten iron rotating, probably. That sounds like a current, right? Okay, but we know there is one because compasses. All right. So the other thing is north poles feel a force in the direction of the magnetic field. Okay. South poles feel a force in the opposite direction of the magnetic field. So north poles are sort of like positive electrostatic charges. South poles are kind of like negative electrostatic charges, if you want to make that analogy. However, they don't interact with the charges unless they do what? What's current? What does that have to do with charge? How do you get a current? Charge over time. But what does the charge have to do? Move, right? Current is moving charges, okay? So stationary charge, no magnetic field. Moving charge, something happens. Now we have a magnetic field, okay? So if we don't have, if we just have charges, we have what kind of field? What kind of field do charges create? Electric field. So whether the charges are moving or not, we have an electric field, okay? If the charges aren't moving, we only have an electric field. If the charges are moving, now what kind of field do we also have? Magnetic field, okay? So charges, when they move, generate magnetic fields. Now, if you want to get real confused, the reason charges that are moving create magnetic fields is actually relativity. It turns out that the electric field and the magnetic field are actually the same field, and we'll talk about this at the end of the class, okay?
Wait, what?
Yes. But because of reference frames, you'll always generate the same force no matter what reference frame you're in, but whether it's generated by the magnetic field or the electric field depends on which reference frame you're in.
So magnetic fields are electric fields?
Yeah. That's why it's called electromagnetism, and that's why it's called the electromagnetic force. It's just kind of two sides of the same coin. But forget all that for now, okay? Or keep it in the back of your head as like a fun finale to the class, all right? But what I want you to remember now is what are, if we just sit in the laboratory frame, we're not moving, we're just watching charges that are stationary and then charges that are moving relative to us, okay? Stationary electric charges create electric fields. Moving electric charges create electric and magnetic fields.
So if you were standing on moving electric,
It gets weird. So if you're moving at the same speed as the charges,
stationary.
yeah, then you'll see an electric field, which will generate a force that would be the same as if you stood still and the moving charge generated an electric and a magnetic force. Same force, different causes. Okay, and that's special relativity. If you want to learn more about that, stay tuned until the end of the class, and also in 210 we go into it in a little bit more detail. Okay? Anyway, a Tesla is an expensive car. No. It's 1 Newton divided by amps times meters. Yeah, very easy to remember. We have great units in this class. They're not horrifying at all. So, all right. This means we have to add some notation for talking about magnetic field, because it turns out the magnetic field is always in the plane perpendicular to the charge direction of motion. Okay, so if your charge is moving this way, it generates a magnetic field this way, right? So remember the wire pointed this way and the magnetic field was this way. How many dimensions is that we have to keep track of? 3. Okay, this is 1 dimension, and then there's a plane in this direction. So almost all magnetic field problems involve 3 dimensions. And if you want things to be perpendicular, what kind of vector math do you end up having to use? Cross product, okay? So we've been in dot product land for the whole beginning of the class. Welcome to cross products. And what happens when you throw in a cross product? You go the wrong way. You have to use the right-hand rule, okay? Because perpendicular, right? If you have a plane, if something's perpendicular to that plane, it can either be up or down. And you have a 50-50 chance of guessing correctly, but your chances are much improved if you correctly use the right-hand rule. Now, there's several versions of the right-hand rule, but they all depend on the fact that you use your right hand, okay? And we'll talk about what they are as we go on. But here's some visualizations of how things look. Basically, I want you to think about vectors as, I don't know if you watched Robin Hood ever, but here's an arrow with some feathers, okay? So if this arrow is coming at you, what do you see? The point, right? This is the arrow about to shoot you in the face, okay? So be afraid, okay? If the arrow is going away from you, you see the feathers. Those are X's, okay? So this means out of the page. This means into the page. So for a field that covers a large area of space, right? Out of the page, into the page. If you're talking about a wire with like a current, it's the same notation, but obviously you only have to draw one. So this is out of the page, this is into the page, okay? Now this gets tricky as we do these sorts of things, but we'll talk about it. So here, let's say we put a current going into the page, okay? So let's practice some right-hand rule, and we're going to guess which direction that so your thumb is your current, okay? You want to point your thumb in the direction of your current. Your fingers are now perpendicular. They're in the plane perpendicular to your current, okay? So if this is the plane, then your magnetic field is in the direction of your curling fingers. So you go like this and like this, okay? So which way do we think that the magnetic field is going to go? Clockwise or counterclockwise? Clockwise, okay? So this magnetic field, and okay, could have animated that better, ends up going clockwise, right? And it looks something like this, okay? So these are your magnetic field lines. What do we notice about these lines?
Circles.
They are circles. They start and end at the same place, right? So they don't go off into space. They don't diverge from this point. They go around it, okay? What do you notice about the density of the magnetic field lines?
Further away you get.
Yeah, it's stronger, closer to your current, okay? Probably drops off like, I don't know, inverse squared, okay? Surprise, surprise. These are magnetic field lines. The book and I try to draw these in blue, and the electric field lines are generally red, and this won't be important until we do induction, at which point it will be very important so you know what the fuck you're talking about.
So should we start bringing colors?
You don't have to, but
Should we?
yes. Colors help a lot in these chapters as you try to keep track of a lot of different things, because otherwise you have to label everything really carefully. Use the right colors, use the same notation. It's easier to keep track of. We generally also do current in purple. Unfortunately, sometimes on the board I won't do that because it's really hard to see purple. This chalk just doesn't like to show up. So, I know someone's going to make some whiteboard comment. Whatever. Okay, so right-hand rule. Just formally, the thumb is in the direction of current. Your fingers curl around. Now, this actually works in two different ways, right? If your current is curly, okay, so let's say you have a circle of current. So we'll see if we can see can you see that? Yeah. Kind of. Okay, so let's say the current is going this way. What do you think the magnetic field looks like? Where is it going inside?
The board.
So, you can look at current, you can use the right-hand rule in two ways. So inside the loop, right, you can say you're going to curl your fingers in the direction of the loop. That means your magnetic field points in. But what this really looks like is actually way more complicated, okay? Because if you also follow this thing, that means it's going in here, right, and coming out in here, coming out here. And what that really looks like is it's kind of a loop like this. So all of these guys have this.
Wait,
And
what?
it goes, yeah, I know.
Like a donut.
It's like, yeah, it looks kind of donut-y. It's not easy to draw.
So it's like a tube?
Well, these are the magnetic field lines. So around each current, right, you have the circles. But if you want to know the magnetic field at a particular point, everywhere in here, right, it's going to look something like this, and everywhere out here, it's going to look something like this.
I thought
But
what we
the
did
actual
was
lines, right, if we just look at a cross section, the actual lines are going like, yeah, like this around the loop. Okay? So if you have a loop of current, you also keep loops of magnetic field going around it. So the right-hand rule works in two ways. If you curl your fingers along the current, it'll tell you what the magnetic field's doing in here. Okay, that means it's going in. But if you want to get the whole picture, you actually have to say, okay, so this is going like this, okay, where it goes into the page, then comes out of the page, into the page, out of the page.
So you're doing the right-hand rule to the magnetic field.
No, I'm still using yeah. This works both ways, right? If something's curling, whatever thing is not curling is used by your thumb. So you can either point your thumb in the direction of the current, or you can point your fingers in the direction of the current. Okay? And both of those, the other thing will give you the magnetic field.
So those are both magnetic fields.
No, this is current.
Oh, so it's current. Okay.
Magnetic fields.
Okay.
Okay, so this is E, right? And this is current. What is happening?
I don't know.
Is that your mom again? All right. So, either your thumb in the direction of current and you curl your fingers around the wire to get the magnetic field, or your fingers in the direction of current and your thumb gives you the magnetic field. Either one is fine. The main thing is, which hand do you use? The right hand. Okay? Yes. Let's try this. Now this is worth thinking about because if you can't figure this out, it'll be troublesome.
He's correct.
Yes, much better. So it's going to be out of the screen. Now, what you want to do is right hand rule-wise, right? You point your thumb in the direction of the current, and your fingers tell you which way the circle in the perpendicular plane goes. So if this thing were coming straight at you, right, you want to visualize that there's big circles. So it would come out here, out here and go in here. So out here, in here, if you have a half circle. Okay? So this field is going to be like this, all right? Because it has to be circles around this wire. Now, start visualizing this, okay? If you just depend on the right-hand rule, the right-hand rule is just a tool to help you visualize this big picture. When you look at this, you shouldn't just see what the magnetic field is here, right? Even though most of the time we're only going to need to worry about the magnetic field at a particular point, okay? This is not all the information, though. There is, if you draw the magnetic field vector at P, it's just pointing out of the page like this.